So one of the questions was about how this all comes together, and there seemed to be some confusion about we estimate phi and tau, and then we have that value for a species, and then so what do we with it? What do we do with it? How do we get estimates for all the rest of the data that we haven't used? So you can think of it this way, that you have your species data. This is not tabulated in any way at all. This is just the counts table where you have species, this distance, this interval, this many at this station, right? So this is that long table that we have used with xtab to create distance, time, or just the total count, and lots of species, lots of surveys. Now you can imagine if this is the same project collected under a different protocol that allows you to have multiple time and distance intervals, maybe you're just looking at this overlap where you have everything and you can just take that data and do anything you want with it. But sometimes there's going to be a project where you only have time information, or you only have distance information, or you have both, or you have none. So this is that large table, lots of projects. So you have a subset that you can use to fit this removal modeling. There's a subset that you can take and fit the distance sampling model, but eventually you want to talk about all of that, because without offsets, what we would do, just somehow get the total count for a single species, get a set of predictors matching these rows so that at each survey we know tree cover, temperature, elevation, and so on. And this is what we would then do in a naive GLM. And once we have these results, then we might replicate the process for many different species. So X would probably stay the same, and Y is going to change depending on whether you are looking at robin, an ovenbird, Tennessee warbler, or whatnot. And what we are trying to do is come up with this matching offset for everything. So how do we do that? We take the removal modeling estimates and the distance sampling estimates and calculate this P and Q based on that cumulative density function. And if you don't know time of day, because somehow the nodes got lost or there's a smudge and you can't figure it out, then you might just fit a constant model where it's not a function of day, just a constant phi, and you might be able to still use that number without knowing what day the survey happened on. Otherwise, you would use the model to predict phi for a given day and turn that into p using e to the 1 minus e to the power total duration times phi at that location at that time. So this way, this is not a constant anymore, but for each survey, and this is not quite right that I drew these lines. So this is really, the rows are matching the surveys and not this long table which has surveys / species, right? But you would get this area is either known or you use the distance sampling information to get that area sampled, P and Q. So if you know all of these, then you get the offset, which is the log of the product of these three. And then you take that offset and use it in your model to kind of adjust the intercept to the right level. Does it make more sense now with this little schematic? I'm asking you mostly who asked the question. So how to take the models and make the prediction, and how it all comes together. So if you are really looking at the code, I think you can figure it out, but still, yes, I see that this was a bit maybe fast as I went through that.
No, I think it's fine. I think I do I think I understand what this is going a little bit better. And yeah, no, I think this helped.
Okay. Well, let me know if still you want me to clarify bits of it. But so we take a subset, fit a model, use that model to make a prediction for all of these surveys that we want to use in the GLM, because eventually we're just going to use the total count and some predictors and an offset. So
and we're using the total. I guess the only thing that I'm trying to wrap my brain on is we're using the total count of each individual species. So P and Q is unique to a species, not unique to the whole survey.
Yes.
Gotcha.
So all of this, what we've discussed, is for a single species. The only thing when we looked at multiple species was how to use that information to better estimate tau. That's where we kind of went on a tangent on this, but still we would use that information to get an estimate for a single species and then do the modeling as a single species. When it comes to community, that's a whole different question, and it's like so complicated that my head hurts when I try to think about it, because yeah, it's just whenever you get an aggregate measure, which is like total abundance, species richness, diversity, whatever, then all of this comes into the picture, and how these biases go in different directions, and at the end what this detection error leads to when you talk about taxonomic diversity or phylogenetic, whatever, these fancy metrics.
And also, just on that note too, if I understood correctly, the P and Q are also, they're estimated for each species, but also for each site.
Yes. So if you only have a constant model, you can just repeat the same value. But if you know something at those sites and at those times, then you might change that as a function of that, because so these are function of land cover, function of date and time. So these are information either known because you went out sometime and you know when that happened, or you know that because you did the GIS for these predictors anyways, or you collected that info in the field, which is still fine for fitting the model. It might be harder to make a prediction unless that's really have a nice crosswalk with some land cover feature that you can trust. Yeah, but that's more of a general modeling kind of question, which you need to deal with when you're trying to make a nice looking map. But you might still be able to say, well, forest cover has this effect, even though you can't necessarily show it on the map. So this is the schematic. I'm going to include some of like these images that I created as my little quick way of showing some of this without spending too much time in PowerPoint. So let's go back.
That schematic seems almost paper ready. Really cool.
Okay. I had some slides like this in the past, but I just didn't have time to track them down. I had a whole presentation like years ago about this. So maybe if I find that, I might just include either a link or the PDFs themselves so that you can check it out if you're interested in kind of more the higher level overview of how this all comes together. Because I can see, yes, the code might be daunting at places. So now let's have a look at a species which is still ovenbird, but you might have picked a different one that's close to your heart, and we have it in the data and is not too rare, because otherwise you won't be able to get really nice models for this purpose of learning. So what I'm doing here is I reorder my X data frame, which has all the variables associated with each survey. And I'm just going to order it based on, this is just forest amount. So if I happen to plot this, then it is going to be kind of nicely ordered. And then use those row names to get matching total counts and the offsets. And then also create this capital X, which is the model matrix based on this formula. Right-hand side says decisions. This is the model we are going to fit using various techniques. So my Y is now a vector with a bunch of zeros at the beginning, but we have these counts up to 6. Now we have O, which is our offset. You see these numbers are at the beginning are the same, but if I look at the summary, there's some variation, 0.11 to 0.26. So this is already on the log scale, and we are using 5-minute 100 meter for everything now. So you can pick a different one, but this is kind of somewhere in between. It is not the highest possible count, so it's kind of the middle ground. I just picked it as a why not. And X data frame just has all this information that we had before, but for the sake of simplicity, our capital X, which is what we are going to use for the matrix product with the coefficients, has this intercept, which is all ones, and deciduous forest amount, which is a value between 0 and 1. So that's something we can put on the x-axis and quite easily visualize so that we can see what do we get from the models. Poisson GLM, no surprise here. This is what we did before, just in a more vectorized format to look at multiple of those columns. Right now, we are just looking at one column, but multiple model types. Let's call it MP, capital M as model, P, Poisson, and the same notation goes for density. So you're not just looking at the mean, but all those values that we can predict based on the actual values of the deciduous forest amount, and call it capital D and an indication of what kind of model this was. So we have the total counts on the left-hand side, deciduous forest and the intercept implied on the right-hand side, data equals X. This is where GLM is going to find this column. We have no Y column, at least I think so. Let's just double check, because if we had, that's bad. No, we don't have. So what's happening here is that you have the formula, and GLM looks up these terms inside the scope of this data frame first. So if there's a column called Y or decid, it is going to take it from X. If it can't find it in X, then it is going to look in the parent frame, which happens to be the global environment. And that's exactly where we have Y defined. So you really need to be careful with scoping if you, like me, tend to call everything X and Y and Z, that it might be present in your data frame. And in that case, GLM is going to use that. So then we specify family as Poisson, which also implies that we are using a log link function, and offset equals O. All done. Summary MP. That's pretty much what we would expect based on all those coefficients that we've seen before. And then summary of DP. We have these expected values from lower to higher, 10-fold difference between min and max. That's driven by land cover. So if you want to use negative binomial GLM because you think that this count distribution is somehow under or over dispersed, so if we plot it, we might be able to see it better. So you can see it's kind of going, and here the 0 would be expected right here. If you just imagine this is some kind of Poisson distribution maybe up here, down here, I don't know, but this is way too much zeros. So you can say it is zero inflated, which is not a surprise. It can be due to methodology. It was collected late in the season in a habitat type where detectability is lower. So things like that can drive the excess of zeros, but also there seems to be a few really high counts, which we would not necessarily expect based on a Poisson distribution. So maybe negative binomial is going to take care of this over dispersion, and our offsets might take care of the zero inflation because that's happening due to detectability, not necessarily as a true zero inflation, that there's this occupancy species range, inside the species range is the abundance. So we'll look at zero inflated models in a second, but let's just first try negative binomial. So in the mass package, we have the glm.nb. We can specify offset as an argument, but we can include it as part of the formula. And the coefficients are also going to be on the log scale because this negative binomial model uses the same log length function. So the mean abundance that we want to predict is going to be the same. Take the coefficients, multiply it together with this capital X, and get this D and B. And so the extra parameter we are getting there is called theta, which relates to the variance of the negative binomial. In the Poisson, we have that linear relationship mean equals variance. Here we have mean, and also this theta is going to make it higher or lower depending on whether it's larger or smaller than 1. And we are not really looking at the prediction interval in this sense. We're just trying to see how do we fit these models. What is that mean prediction we can get without including the offset? So here, if you look at it, we have no offset involved. This is a safe way to get prediction without the offset. Otherwise, with GLM, I never know. So when we want to do zero inflated Poisson, again, looking back to these counts, we have far too many zeros. Some of that is likely to come from detection error, but maybe it's a true zero, species is just not there. So we can fit a zero inflated Poisson model, and this means deciduous forest is influencing the count, and for the zero inflation, we are just looking at the constant probability of getting a zero. This can also be a function of covariates, but I'm not doing it right now. Then distribution is Poisson, because in the package PSCL function zero inf, you can fit zero inflated Poisson or negative binomial and include the offset term like this. Before I explain the next line, let's just skip to zero inflated negative binomial. You can see the only difference here is that for the count distribution, we specify neg_bin as negative binomial. Now the prediction is going to be the same for these two, except for specifying the right model, mzip or mzinb. And so when we have a model like this, let's just look at the summary. Now we have count model with intercept and deciduous forest, and the zero inflation model, which is modeling the probability of getting an excess zero. And we have an intercept. This is using logitlink. The count is using loglink. And we can get the corresponding coefficients as coef in zip. You can see count, count, 0. So if I want only 1, I can say give me count or give me 0. So what you can see here, 1 minus p log is coef 0. this is taking this coefficient, turning it into a probability, and 1 minus this probability is going to be the non-zero, which is what we can use to multiply the count part with, because that is just going to affect our expected value. So the expected value here is 1 minus zero inflation times lambda. And this is lambda, which is like what we did before, except we're pulling out just the count specific coefficients, intercept and deciduous, and combine this together with this probability. So the p-logis function, if you have something like minus infinity, 0, 1, plus infinity, and you want to take the p-logis, please. Then that's going to turn this into 0, 0.5, 0.73, and 1. So if I now go q-logis 0, 0.51, then I get minus infinity, 0, and infinity. So this is the logistic link function back and forth. So if you want to turn this intercept into a probability, and 1 minus that probability is going to be a probability of a non-zero, then this is what we will do, and that's 0.81. So the amount of extra zeros that is coming from the zero inflation is around 0.2. The rest of the zero is coming from the count distribution and is due to the detectability, which we are accounting for through the offsets. So some of the count sixes can be, I mean, true abundance 6 might be a 0 because we haven't observed anything. So anything that is higher than 0 can be a 0 or something of a lower count, if you recall that little table. So if I plot again, plot table y, now we have all kinds of sources for the zeros. Some of that is true 0 coming from the abundance part, some of that is zero inflation, and some of that is due to detectability. So it's really getting complex, thinking about why we might get a 0. Same kind of prediction we can do for the negative binomial, because the expected value is going to be the function of these coefficients and not the function of the variance factor. Now this is going to be interesting. I threw this in because sometimes you don't necessarily have count, but you might still use some information to predict P and Q, which is something you can use in a 0-1 context. Because if your 0-1 refers to observing none or observing something at least 1, so in this case, we create y01 as if y is greater than 0, make it 1, otherwise keep it as 0. So you can see zeros are zeros, anything higher than 0 are now turned into 1. So we can use some kind of binomial GLM to estimate this. What makes this special is that we are using the C-log-log link function instead of the default logit. And what this does is it makes the model as if it were a truncated Poisson. Or maybe I should say censored. So anything that is greater than 1, we are just treating it as 1. If you navigate to, in the workshop, there is this etc directory and there's this extras. If you open this up, there's a description about censored Poisson data, and with all the math that I'm not going to explain why the C-log-log function is equivalent of doing this. Let's see what we get. We use this as the response 0-1, same predictor, X, family, binomial, C-log-log. offset. And instead of using the inverse link function of the C log log, we're using the exponential, which is the inverse of the log link, because we are approximating a Poisson model based on a censored data. So let's see how the two compare. Mean dp was our Poisson, and now this is our censored. It's a bit off, but not too much. So you're still talking about density in the same sense, although we might get some bias because by censoring and treating everything larger than 1, we are just saying, well, let's get rid of that information because we don't have it or we don't trust it. So this way, any detection can be treated in this framework. So if you are really worried about double counting or not really knowing if those counts are true, then you can apply some kind of truncation on top of it. So this is just one way. Yes, I think there's a question.
Yeah, sorry, I was just going to ask just a clarification there. So is the reason why you're using the C log log link is because essentially this is still a Poisson distribution. It's not really like sort of the typical binomial distribution. We're just kind of ignoring anything bigger than 1. Is that kind of why you're using that link? I think that's what you just said, but I just want to clarify.
Yes, because you still think that a 0 is a 0 and a 1 is a non-zero. And you think about Poisson, you can express probability of 0 being e to the power minus mean. And probability of non-zero is 1 minus e to the power minus mean. And so if you take these as the probabilities and write down the binomial likelihood, which is then used to estimate the parameters under the binomial GLM, you're going to get these coefficients. But then you are not turning that into a probability of observing a 0 or a 1, but instead of turning it into this mean, lambda. Okay. That's why we are using the exponent instead of the inverse of the C log log. Because this way we can refer to the mean of that censored distribution, which is still the Poisson. So if you imagine, this is how the C log log link function goes, like an exponential function, but at 1 it kind of plateaus off. And the exponential would go beyond. So that's why. All right, so now this is where the fun begins. After simple GLMs, we're looking at GLMM, which is something we covered before. So what we use here, the LME4 package, and we have this GLMer function, which is something you can use to fit models to count data. So not the linear mixed model, but something like log linear with Poisson counts. And why I'm saying Poisson log normal is because the random effects distribution is normal on the log scale. So if you exponentiate it back, that becomes a mixture of Poisson and log normal random effects. So what we do here is use the fixed effect deciduous forest and random intercept based on site ID. Family Poisson offset O. So really the difference is we're calling a different function and there is a random effect. Otherwise, the GLMer specification is very similar to the GLM. Now, when we are making the prediction, we need to be careful. There is no such thing as QF and PLM. Or what you get there is a combination of fixed effects and random effects. 4,000 rows, so I'm not going to scroll all the way up. And then we have this model MPLN. We have random effects. You see here for the site ID random intercept. This is the standard deviation of a normal distribution centered at 0. This is where those intercepts are coming from. And then for the fixed effects, so this is the intercept is what you can think of this is where the random effects are centered around. And when you have the slope effect, that's kind of orthogonal to this. You have that slope.
Peter,
That's here. Yes.
Is this what is called observation level random effect in the literature? And then what's the rationale for incorporating this? Would it be handing over dispersion, or there's another?
The way I like to think about this is we have the deciduous forest amount, but we know we looked at wetlands around the species, and that seemed to be the second best predictor. But we are, let's say, we have things that we are pretty sure are going to drive ovenbird abundance, but we couldn't collect that information. And so this way, if there is still some variation which is not explained by the fixed effect, that is going to be due to something else that we couldn't measure. And as a result, we couldn't incorporate as a fixed effect. Because if we keep adding predictors like amount of wetlands, mean temperature, elevation, eventually we would expect this random effect variance to reduce, maybe to the extent that we don't even need a random effect anymore. So if you want to just account for something that you haven't measured, that couldn't measure, and you still suspect, yes, there is over dispersion, and I don't know how to explain that away, random effect is a good way of looking at it. And in a way, the negative binomial is doing something very similar. Because there, instead of Poisson log normal mixture, it's a Poisson gamma mixture, which has a very similar shape to a log normal, but it's parameterized differently.
Yeah, so
kind of a similar idea.
Yeah, so account for landscape context in a way that even if you knew what landscape context is, you will need to fit fixed effects and make the model more complex. And this way you're accounting for it in a way that is more parsimonious, so to speak.
Yes. Because then you are not saying, well, each of these are different, but I don't know how, but you assume that there must be a distribution around that, and let's try to estimate that distribution. So now if we, where was I? Oh, we jumped over again. Never mind, we'll get back to it. So if I do the prediction and look at this mean density, mean, and the plain Poisson, now this is much smaller than anything that we've seen before. And this is due to the random effects explaining a lot of the variation, because I'm pretty sure this is a large area, it's a complex environment, and it cannot be just one predictor that would capture everything involved in the species biology. So if you capture that through the random effects, then even your intercept might change, and you get this number that now, on average, we get less ovenbirds in the landscape. So if we go back to the GAM, we have a spline for deciduous forest. Otherwise, it's all the same. Instead of GLM, we say GAM. And why I'm using MGCV : is because in another package, NLM or something, there is also a GAM function. So to avoid confusion, I'm using GAM from the MGCV package. Summary. You can get a summary for this spline, degrees of freedom, and then also you can plot MPG. So this is our response with deciduous forest. As you recall, in the plain Poisson, it was kind of the opposite relationship. It kept going up. You can see here that even small amounts of deciduous forest can increase quickly the density. and then it kind of, you see less change. So if you suspect nonlinearity, this is a nice way to capture it using splines without worrying about polynomials. And we get the GAM-based density mean DPG, again, close to the plain Poisson mean. Now, this is an area which I'm not sure that I included all of these packages originally. I kind of just threw this in yesterday. Let's give them some real examples of machine learning algorithms that we are using in production. So these boosted regression trees are being used quite extensively within the Borel-Avian modeling project using offsets. And so this is coming straight from some recent projects with slight alterations. But this is what we do at very large scales. We take the subsets, calculate the offsets, and then fit a boosted regression tree. So let me load these packages. If you can't load them, try installing them. It shouldn't take long. Just install the packages, Dismo and GBM. Probably you already have ggplot2. And I'm just creating this XI data frame with my count involved and some of the covariates. And if you want to do K-fraud cross-validation to optimize the number of trees this is going to fit without spending a lot of time of explaining how regression trees work. So you find splits. So it becomes this very similar step, like simple step function. You find a split along a variable and you say it's lower here, higher here. Find another split, find another split. So what we say here, tree complexity is 3. So we are looking at 3 splits at a time. That's one tree. Repeat it many times. That's going to be dictated by the learning rate. So how many trees you want to fit all together. And all these simple trees are then combined together into one prediction. So the next tree is always trying to explain the residuals. So you take one tree, calculate the residual, fit a tree on the residuals, and so on. So you keep adding trees to the remaining variation. And then if you do that 10 times with cross-validation based on that error rate, you get a sense of how many trees you need. So this takes quite long. I'm not going to do that, but here's the code if you want to do this gbm.step from the Dismo package. And there are lots of literature about this explaining what it's doing and how to tune these parameters. And this is how you would do the prediction. If you just want to get one run without the cross-validation, you can directly call GBM from the GBM package. And I'm referring to these as BRT, like boosted regression trees. But it's also called GBM, generalized boosting machines. So what we need here, we just tell it 1,000 trees, that's what I want. Interaction depth is like this tree complexity. Shrinkage is like the learning rate, but I used a different value. Back fraction the same. Distribution Poisson, and notice that we included the offset as part of the formula. So what we say here, y is the response, dot means everything in this xi data frame, plus use an offset. You can also use multiple cores. And if now I run this, it is going to just print out a bunch of things related to the trees. And because I said verbose equals false, I don't see any of that. And then we can use predict.gbm. This is the model we just created. And then we need to tell how many trees we want to combine for this prediction and give us the values on the response scale, which is that exponent coming into the picture. And this is the data set we want to use, which is the same that we've used to train the model. Now it says GBM does not add the offsets to the predicted value, which is exactly what we need. So thanks for verifying that. Mean DBRT, close to what we would expect based on GLM or other methods. I included some other functions where you can look at these trees and get a sense of variable importance. Deciduous forest comes on top, 90%. That means 90% of the 1,000 trees included deciduous forest as one or more splits. Rest, coniferous wet, coniferous forest, less often, but still second and third. And then marginal effects plots are really useful. You can do these for any other types of models, but for tree objects, there is no easy way to do other than marginal effects plots. So you can't easily, well, I guess you can condition, but it requires more work because there is no function to easily do that unless you have experience with other packages that I don't know about. And then this is just going to be a ggplot image of the top 12 predictors. Oops. BRT. There it is. So you can see all of the lines are pretty flat because I forced the scale to be the same. But deciduous is really having that effect that we've seen from GAM. It is not strictly linear, it levels off, but very similar to what we've seen before. So this is how you would do boosted regression trees. And these are the kinds of families that I wanted to cover. If you want to do MCMC, I can include links, but I'm not going to cover that because that's a whole different topic. And conceptually, it's very similar to the mixed models that we've seen, like the GLMM type example. So if you want to compare everything that is parametric, so we can't really do AIC for tree regression, but here you can see that the log normal, the mixed model was the best because it just captured more of the variation through the random effects, and that shows up in the AIC. And then we can look at all the means. We can also plot the relationships, but I'm not going to spend time on it.
Sorry to interrupt. Are you sure it's not the GAM, the Poisson GAM?
Oh, you mean
for the lowest AIC?
Let me check. For
because it's 9.2.
Oh, right, that's correct.
Okay, good. I just
right.
wanted to make sure I wasn't
yes
going. Thank you.
No, you're not imagining that's the case. Sorry about that. Yeah, if you add that 1 minus min. What did I do? Oh, yes, because I need just one column. AIC. Yes. So it's the GAM where you see the 0.